Let me start by thanking the organizers again for organizing this wonderful workshop and also for inviting me. So I'm actually a computer scientist. So majority of my work is actually designing computational algorithms and machine learning techniques for information design and their real world applications. This talk is about solving information, which I think is another very interesting application of information design. This is actually still a working paper, and I would love to hear your feedback. And if there's anything I'm missing or due to my ignorance, definitely feel free to point them out. Okay, good. So motivations, selling information actually already happens a lot, in our daily life. For example, if you are a credit report company, you might want to sell information to some loan company or to a bank. If you hold geographical data about customers, you might want to sell it to marketing companies to help them to better target the users. Or if you ever have bought a used car, you might have done the used car inspection, and that's literally try to buy information about the car condition of the used car. And if you go to financial advisors, to get some advice about which stock to investigate, that's also essentially purchasing information from the financial advisor. So the model we study is actually very simple and clean model. So we have one seller and one buyer. The buyer is a decision maker who faces a binary decision. So he have an active action, which is action 1, and a passive action, action 0. So the active action could be, you want to, if you're a loan company, maybe to approve the loan, or maybe to buy a car, or maybe to invest some stock X. So that's your active action. And passive action is to not do this, right? So therefore, your payoff for the passive action is always 0. It's because you are not doing anything. But your payoff for the active action is V, is a function V that depends on Q, which is the state of the nature, and the T is the buyer's private type, right? So I use the notation Q as opposed to typically theta or omega because I want you to think about the Q as like the quality of this active decision. So that's Q. The only assumption we're making about this payoff function is we're assuming it's going to be linear and non-decreasing in the buyer type T. So what does that mean? That literally means there exists a function V1Q and a rho Q such that the VQ can be written in this linear format, where V1Q is non-negative because we're assuming it's non-decreasing in the buyer type T. Okay, and this, I should point out that this utility assumption has been widely made in some other persuasion literature as well. Okay, so in this talk, I'm going to assume this linear structure for the payoff function V. So, and we don't impose any assumption on the signal on the state of nature space. It's kind of arbitrary measurable set, capital Q. And the buyer's type T is drawn from a continuum interval from T1 to T2. Therefore, T1 is the smallest type, T2 is the largest type. The information structure is the following. The Q, the state of nature Q, is drawn from a prior distribution, and the buyer type T is drawn from another distribution, and they're independent. That means the buyer's type T is some kind of private characteristics of the buyer and have nothing to do with the information. Or alternatively, you can think of buyer gets some kind of information from a completely irrelevant information to Q, some other things. And like the standard information design literature, we assume the seller, who you should think it as a sender, observed the realized state of nature Q, but the buyer holds his private type T. And the question we're looking at is a mechanism design question. How can the seller optimally sell her information about this private observation Q to the buyer? Any questions here about the model? Okay, good. So here's a concrete example. Let's consider, a credit report company want to sell the information to some maybe loan company. So the buyer is therefore a loan company. His action is to approve the loan of some user or not. So if not approving, then nothing happens. His payoff is 0. And if he approved the loan, the payoff maybe have some kind of linear structure like the following, where it's QT minus 2, where you can interpret the Q as some kind of payback rate, depends on the credit history of this user. And the T is the gross income, gross profit from this, this particular user he's borrowing to, because that's private information to the loan company, because it depends on what is his interest rate and how much money he borrowed to the user. And you can think of 2 as the operation cost. Towards the end of this talk, we're going to see what will be an optimal mechanism for selling information to this loan company. Okay, so related literature, the most relevant to us is by Bergman et al. In 2018. Dirk actually might also be here. So the overall model we're considering is almost the same as their model, except that in their model, there were finite state space and there were multiple buyer actions. But in our case, our state space can be arbitrary, so it doesn't matter. And but our buyer only have 2 actions, an active action and the passive action. And the state of nature only affects the payoff of the active action, because passive action always gives you 0. And moreover, in the Bergman et al. Example model, they're assuming the buyer actually has private information related to the state of nature. Therefore, the buyer type is somehow correlated with the state of nature, but we are assuming independence. So in some sense, our information structure is actually is simpler. And that is also the reason that we will be able to get a closed form optimal mechanism solution. Whereas in the previous work, it's primarily looking at the properties of the optimal mechanism. Another related work is also by Bergman and with Bonatti. They're looking at selling the realized state directly. So you cannot do the signaling scheme and things. But in our case, we're looking at the selling experiments, or you can call it the signaling scheme. Classical works also at selling, look at the selling information to multiple agents when they trade an asset afterwards with common value. And there were also some algorithmics. So this is clearly related to Bayesian persuasion, except that the seller don't have a utility, but just have just try to maximize revenue. It's particularly related to persuading a privately informed receiver by collotillion, and I myself had some algorithmic result on this. And there's also some computational study, but these are all mostly algorithms without closed form characterization. Okay, so when we look at designing mechanisms, the first thing we might want to think about is what is the design space? What are the possible mechanisms that I'm going to consider? In this paper, we only focus on mechanism that price experiments. So in other words, you cannot price the realized state. You are pricing the experiment itself. This is similar to the previous work. Therefore, following the standard revelation principle type argument, it's very easy to see that you can, without a loss of generality, restrict it to a manual, which is, pi t is to a manual pi t pt for every buyer type t, where pi t is an experiment for type t. It's literally the signaling scheme maps the state space to a set of signals. And PT is a buyer's payment. It's a real number. And without a loss generality, each type would be incentivized to truthfully report their type. So with this kind of simplification by revelation principle, we arrive at a concrete design question. That is, how can you design an incentive compatible manual of a signaling scheme and the payment to maximize the seller's revenue? Okay. Okay, so the first question you might ask yourself is how it differs from classical mechanism design for selling the goods. There were at least 2 major differences. The first is that here we're selling the experiment. So you can intuitively think of each experiment as like an item. Therefore, in that sense, you can really, it's really like we're selling infinite many possible items, because you can, in fact, you can even design in the item because you are designing the experiments. But the good news, of course, is that the signaling scheme have spatial structures. It's not just an arbitrary item that you are selling. Another key difference is the individual rationality constraint. And that turns out actually to be crucial because it actually leads to a very different format of the optimal mechanism. In particular, in classical mechanism design, IR simply means, if you participate in the mechanism, your utility, your surplus have to be at least 0, because that's better than not participating, in which case you simply get 0. But the problem here is different, because even you don't participate in the mechanism, that means you without any information, your utility is actually positive, because you do have choice among 2 actions, 0 or 1, and your utility for action 1 is your expected utility for action 1 without any additional information. And that is the V bar T that you can just write down by taking the expectation here. So V bar T is the expected utility without additional information. And this means, when you are participating in the mechanism, your utility have to be at least this amount. And this turns out to be a crucial technical difference that poses to the mechanism design problem. With this, so we can proceed to describe the main result of the paper, which is basically a closed form solution to the optimal mechanism. It turns out that in our optimal mechanism, the threshold experiments, we only use the simple threshold experiments. What do I mean by a threshold experiment? Well, a pi t is a threshold experiment if there exists a threshold theta that depends on t, and the pi t simply reveals the rho q is larger than theta t or not. So that's kind of the experiment. And note that here the threshold is on rho t, not is on rho q, not the q itself, because q itself can even not be a number, because q is arbitrary, state of nature space. Rho q is a real number, and this is because of our linear utility function assumption, which depends on rho q. So to state our mechanism, the only notion we need is a few notions of virtual values. Let me start by recall the standard virtual value function developed by Milson in his optimal auction design, which have this format. It's t minus 1 minus capital Ft divided by little ft. That's pretty classic in auction design. We're actually going to call this a lower virtual value, which exactly as Milson was deriving. The terminology lower is because we have another notion which we call upper virtual value. And you can see it's almost the same as the lower virtual value, except they don't have the 1 divided by ft term. And the name upper and lower is really because the upper virtual value is always greater or equal to t, because it have a t plus a term. And the lower virtual value is always less or equal to t, because it have t minus a positive term. And the most interesting part is the optimal mechanism actually depends on a novel notion which we call mixed virtual value, which is a convex combination between the upper and the lower virtual value. And that somehow naturally arises at the optimal mechanism. Okay, it's just a convex combination. So a virtual value function, just like in the standard notion, is called regular if it is monotone increasing in t, and if phi t, any virtual value function, if it's not regular, there's a standard ironing technique that can convert it to a regular virtual value function. In Milson's work, he developed it for lower virtual value, the ironing techniques, but it's generalized to arbitrary function. A crucial technical lemma that we will need is for any fixed t, the iron virtual value, the mixed virtual value, phi c t, is actually monotone decreasing in c. This is pretty intuitive for the original virtual value, because c is the fraction you are mixing the lower virtual value, which is smaller. Therefore, c is larger. If c is large, then your virtual value is going to be smaller. But it turns out that actually it's kind of technical to prove it for the ironed version, because the ironing procedure is kind of complicated procedure. You need to lift the function up to its integral first, and then convexify it, and then get it down to by taking the derivative again. And somehow it turns out that after like a technical argument, you can show this monotonicity will be maintained, and that will be important for the result.
Haifeng, sorry. You mentioned that the V of Q of T is linear in T. Have you, are you going to assume something else about how Q affects V and rho? Or not?
Oh, no. So we're, that's the only assumption we need. We don't impose any additional assumption.
Okay. Thank you.
Yeah, thanks. Okay, so now we're ready to state the optimal mechanism. It turns out that the optimal mechanism depends on two problem-related constants, which is, I call it V low and V high. I'm not expecting you to look at the constants. It doesn't have a nice interpretation, so it's not particularly important. The only thing to note is V low is always less than V high. Okay, so then the optimal mechanism can have the following format. It turns out that the mechanism actually depends on V bar, how large V bar T2 is. Recall that V bar is the buyer's expected utility for action 1 without any additional information. So it's like a benchmark utility. So if V bar T2 is less or equal to VL, V low, then the mechanism with the threshold experiments, which the threshold is simply the negative of the lower virtual value, and with the following payment function represents optimal mechanism. This payment function, it's kind of have some kind of intuitive explanation, but let me try to explain. So the first term here is actually the utility of action 1 under the experiment pi t. So that's just, if you look at it, it's just the integral over by taking expectation over Q. Therefore, the second term here is actually the additional utility the buyer gets by participating in the mechanism, because it's a difference from between his utility and the payment. And as I said, a crucial constraint we have to satisfy is the IR constraint. That is, his utility for participating in the mechanism should be at least his utility without participating, which is the max between the two, as I said before. And so the crucial technical challenge in proving the result is really to guarantee this kind of IR, as opposed to the classical IR constraint, which simply says this only needs to be non-negative. And you can see this technical difference actually leads to a different format for the other case, which is when V bar T2 is greater or equal to the V high, then the optimal mechanism is going to have the following format. It's also a threshold experiment, but with the upper virtual value. Okay, and you can see the payment function have a slightly different format, because here I'm actually using the integral is integrating from a different domain from T2 T2, and at the end I need to minus V bar T2. Okay, this kind of difference is really because I have to handle the IR constraint, which somehow turns out to be different, leads to this different format. The more interesting part is actually when V bar T2 is at the middle between VL and VH. And it turns out that in this case, the mechanism gonna have a threshold experiments that depends on the mixed virtual value, which is a phi C, and for some constant C that is carefully chosen in the following way. So if you look at here, it's an integral that depends on our mixed virtual value function phi C equals V bar T2. Okay, so here is a place where we need the monotonicity of the mixed virtual value function in C, because that monotonicity actually implies the left side is going to be a monotone function as well. Therefore, I can really binary search for the C that exactly hits this V bar T2. Therefore, prove that it does exist always. So that's basically what the mechanism is like. Questions here? Okay, so I want to just add a few quick remarks. This kind of threshold mechanism actually common in real life. For example, if you do car inspection or maybe stock recommendation, the information seller could have only need to reveal, your car passed the exam or didn't pass the exam, or tell you, deserve the purchase or not. And the optimal mechanism turns out to actually have personalized the threshold and the payments, which are tailored particularly to accommodate the different amount of risk that every buyer type can take. We also have kind of example to show that if you restrict the experiments to be the same for everyone, then your revenue actually can be arbitrarily worse. But the welfare actually turns out to be optimal in this case, because you can show if you are only allowed to use a single menu, then you're going to reveal all the information to the buyer. Okay. So as a byproduct, it turns out that the optimal mechanism also gives us some kind of some kind of characterization about what what are some properties about the optimal mechanism. For example, we can show that the buyer surplus is actually increasing for T from T1 to T bar and decrease for T from T bar to T2, where T bar is a particular type, satisfy V bar T bar equal to 0. So here's a figure that you can see. So this is the T bar. So, and the intuition, so what is this T bar? T bar is the guy whose utility for action 1 is also 0 when he have no information at all. So therefore the intuition here is that why this guy gets the maximum surplus. So the intuition is the following. So this buyer is a person who is completely have no idea about whether action 0 or action 1 is better for him, because both of them have utility 0 for him. And for all the other type, they have a better idea about, whether I should take action 0 or action 1, at least a priori. So that is the intuition that why this particular buyer type is going to have the maximum surplus from the mechanism. And so in this figure here, we can see that the buyer type T1 have the surplus 0, and T2 have a non-positive surplus. That actually turns out to be just one of the case. It turns out that this is the case for case 1. And for case 2, buyer T2 actually going to have 0 surplus, and T1 will have a positive surplus. And in case 3, both T1 and T2 both of them are going to have 0 surplus. So I probably only have a few minutes left, but here I want to give you, here I want to give you a kind of rough intuition about why the mixed virtual value actually arises in the case 3. That can be explained from these 3 figures at a high level. So essentially, the fundamental reason is that the seller's revenue can be expressed in different ways. So one way to express the revenue is it can be a function of T1 surplus and the signaling scheme. So in that case, another way to express the revenue is that you can write it as T2 surplus and the signaling scheme. And they have different expression, but they're actually equivalent because they're all the seller's revenue. And it turns out that in this case 1 I'm drawing here, it's actually a lucky case. That's the case when, if you set T1 surplus to be 0, T2 surplus happens to be positive. So in that case, I'm pretty happy because I don't need to worry about the IR constraint anymore because T2 just happens to be positive already. But the bad case is when T2 surplus actually become negative. So in that case, my mechanism is not feasible if I set T1 surplus to be 0. Well, in that case, I might try my luck for another case where I express the revenue as T2 surplus as a function of the T2 surplus, and that is case 2 here. If I get lucky there, then I'm also done. If lucky means I get a positive surplus for T1, in that case, I don't need to worry about IR. But I may get unlucky there as well. So in other words, I may get unlucky in both cases. So that is where I need to worry about the case 3. And the idea here is basically try to mix these 2 cases by do a convex combination of these 2 curves so that they're going to have the same bottom. And then I shift them up to kind of make the surplus at the T1 and the T2 both to be 0. And that's exactly the reason where the mixed virtual value arises. So another property that might be of interest is we find that the buyer payment is actually increasing in case 1, but in case 2, his payment will be decreasing in the optimal mechanism. Where in case 3, his payment will increase first and then decrease next. I guess the punchline I want to mention is that these properties actually turns out to differ from the Bayesian optimal mechanism when you were selling a single item. There, I think that you typically would get a monotone increasing as the type increases. Okay, so for the remaining of the time, I'll just give you a simple example about what the optimal mechanism is roughly like in a concrete instance. So this is the credit score example I gave before. So the buyer's pair function for action 1 is qt minus 2. Let me assume Q is draw from 0, 1 interval uniform at random, and T is draw from 2, 3 also uniform at random. And it's very easy to verify that this is actually the case 1 in the optimal mechanism. So it turns out that applying the theorem, you can get the following optimal mechanism. So the mechanisms are following. For any buyer type T that is at most 2.5, which is actually the middle of the, the middle point of the type interval, the optimal mechanism actually going to charge 0 for this buyer, and then reveals that Q is greater or equal to this threshold or not. And you can see that if T is less or equal to 2.5, this threshold is actually always larger than 1 because the bottom is going to be smaller than 2, and therefore this entire threshold is larger than 1. And that means, the seller going to tell you Q is larger than some like 1.2 or 1.3, but that literally reveals no information because you already know Q is between 0 and 1. In other words, in this case, the optimal mechanism is gonna charge you 0 and also reveal no information to you. And when buyer type is larger than 2.5, and that's the non-trivial case, it turns out that the optimal mechanism is going to charge you this amount, which I don't have any intuition. It's really just calculated from the mechanism and reveals that still it's kind of the same threshold. But now you can see that this threshold will reveal non-trivial information to you because when T is greater than 2.5, this threshold is less than 1. So you will get an informative signal in this case. I think so. And just a quick note is that the optimal mechanism actually sometimes reveal no information to some buyer types. I think that's pretty much it. The summary is that we give a closed form solution to the optimal mechanism to this particular problem. And the optimal solution relies on a new concept of mixed virtual value. And it also, we believe that the result might shed light on some kind of how can you personalize the experiments and prices for various information solving problem, like you do car inspections or house inspections or credit reports, or maybe you can sell your machine learning prediction results and things like that. And that's it for the talk.
Thank you very much. Any questions?
So I think if I understood correctly, the example that you gave is an example which was just one structure that I sell and I charge a price for this structure, right? Is it correct? Like I sell the same, I reveal the same thing to?
No, you are revealing different thing because it depends on the type T. So if you tell me your type
yeah,
T,
I reveal if Q is, okay.
Yeah.
And for which, what would be the functions for which you would, the optimal structure would be, the optimal selling information would be such that I'm just going to propose the entire information and charge some price for it. This is what you call the case in which I give the same thing to all type, right?
So I think in general you cannot, you actually wouldn't see the same experiments for everyone in the optimal version. There is a case where you will see that everyone's signaling scheme going to be the same, which is a reveal for information. That is a case where you are only allowed to use a single experiment for everyone, so you cannot discriminate them.
Okay, but it never pops up as the optimal thing in your model.
Yeah, that's right. Yeah, in our model, it almost never happens.
Okay.
Yeah.
I wanted to ask something. I see in chat also it comes from the listeners about the linearity assumption, but I also wanted to ask about the monotonicity that how crucial that is. I mean, the fact that it's always goes in the same direction. The effect of Q, right? Is
right.
always in the same direction. So how crucial are those assumptions? I mean, I guess that for closed solutions, they are very important. But the question is whether they are really something that without it you are completely lost, or you have to do a little more work.
Yeah, good. So that's a good question. So for the monotonicity assumption, that's something that we're actually trying to think a little bit more. I feel that's not the crucial part. If it is not monotone, we feel like the idea probably would still work. But for the at least I think the intuition seems to kind of all go through. But for the linearity assumption, that can be slightly generalized to a separable assumption in the sense that T and Q are kind of separable. But the separability is important for the results. Yeah, that. So let me take it back is to answer the question in concisely, the linearity assumption is important. Yeah.
I see. And if you were for, I mean, you said that in a sense, it's like having an infinite set of goods that you are selling. Essentially, it boils down to that. The question is, suppose you have to limit that to some, by making some limitations. I don't know what, again, I'm just completely in the dark. Yes, I don't have any good ideas, but maybe there is some useful way to say, you know, not everything is feasible and there are some things limiting what can be done. I don't know. I don't know what's a good example of that, but that may be.
Yeah, that's a good question. Yeah.
That may be useful. I don't know. Again, it's just a complete shot in a complete dark. Yes.
Yeah, I guess, you know, your pricing and information structure has a little bit the flavor of nonlinear pricing. Basically, you know, you provide a quantity of information that is continuous, and you could ask yourself, how well can you approximate a continuous nonlinear pricing a model with a finite menu pricing model? And I think there are results on that that you know you could use or apply, which I think is quite interesting. And the multiplicative structure might actually help you to get results there on approximation quite a bit.
There could you you were saying the linear structure can be,
or the multiplicative between the T and the V of Q, you know, I think that would help you if you wanted to, as Celsius suggested, to get some approximation result. How well could you do with a finite number of items in your menu? You know, you often don't offer a whole continuum of information structure as a data seller. You offer, you know, a big bundle or a small bundle, and so I think your setting is sort of, you know, commensurate or would lend itself to such analysis.
Yeah, I see. Yeah, that's right. Yeah, that's right.
Haifeng, have you thought about the relationship between what you do here and the earlier work by Lewis and Sappington and others on countervailing incentives in mechanism design? Because when I see a outside option, which is type dependent, I think about countervailing incentives, where the emphasis there is that some types have an incentive to overstate and some to understate. And my interpretation of the relevance of the lower and the upper virtual value is also makes me think about countervailing incentives.
I see. Yeah, we didn't look at that. I would love to take a look at that afterwards.
I'll send you a reference.
Sounds good. Yeah, thank you very much.